guys, we're going to start looking at limits. That's the very first big concept that we're looking at in calculus. So you may have talked a little bit about this in pre-cal, but we're just going to go over this again. So here we have a graph of f of x is equal to 2x squared plus 5x minus 3 all over x squared minus 9. You can also see that there is a hole at negative 3, 7, 7, 6. So just a real quick note on that. This right here can be factored to be, it's 2x minus 1 times x plus 3. And then the bottom is a difference of squares, so that's x minus 3 times x plus 3. And you can see that they have a common factor, and those divide out. Don't say cancel. Never say cancel. Don't say cancel. It's like a bad word in math, okay? So don't say cancel. Say divide out. Okay, so they divide out, and so I'm left with 2x minus 3 over x minus 3. And so you can see where we would have an issue with that hole there. So that's just kind of a heads up. So that's why we have a hole at negative 3, because if I were to solve that equal to 0, there's your hole. That's just a little side note. We're going to get way more into that a little bit later, but just kind of sort of giving you a little bit better idea of that. So so here we go. Here's a pre-cal statement. So as x approaches negative infinity, so some sort of like beginning behavior kind of sort of, the graph of f of x is actually going to be approaching 2. So how we say that in calculus is that we would say the limit as x approaches negative infinity of f of x is equal to 2. Okay, so that's how we would say that. So what we're saying is that as this graph gets larger, and as the x values get larger, I say larger and larger in the negative direction, then your graph is going to get closer and closer and closer and closer, almost touching 2, never touching 2 because we have a horizontal asymptote there. So then as x approaches positive infinity, the graph of f of x is going to approach 2 as well, coming in from this way. So again, writing that in notation, the limit as x approaches positive infinity of f of x is going to be equal to 2. Now, as x approaches negative 3 from the left, so as x approaches negative 3 from the left, what is f of x approaching? Well, we know that from this little signal here. We know that that's approaching 7, 6. Okay, even though there's a hole, our lines are still going closer and closer together. So then, I say lines, I mean our function values are still coming together, kind of converging at a certain point. At that point, negative 3, 7, 7 over 6, but there's just a hole there. So as it approaches from the left, we're going to get values that are closer and closer to 7, 6. So this is a little different way to write this. So what we're going to say is the limit as x approaches negative 3 from the left. So that little negative looks like a little exponent negative, like you're like, forgot a number. No, we just write it like that. Of f of x. So that tells me I'm looking at the negative side of that, or on the left side, the left behavior, I guess you could say, of that is going to be 7, 6. And then same thing for as it's approaching from the right, it's still approaching 7, 6. So we would write this as the limit as x approaches negative 3 from the right of f of x is also going to be equal to 7, 6. So since those meet together, we'll learn about that a little bit later. So then as x approaches positive 3, from the left, so we would write that as the limit as x approaches positive 3 from the left. We still write a negative sign up there of f of x. So from the left is going to be negative infinity. And then the same thing from the right, the limit as x approaches 3 from the right of f of x is going to be equal to positive infinity. So we write that as positive infinity. So based on this information, hopefully you can basically see that the limit as x approaches some number a of f of x is as x approaches a. So whatever that y value is, that's where our limit is getting to. Okay, so let's take a look here. So what we have here is, you can see we're going to look at this as a table, and then kind of again as a graph. So what we have here, we have our still same function that we just now had. Okay, so we're not changing functions there. So we're going to complete this table. So negative 1,000, when x is negative 1,000, f of x is 1.995. So I'm going to go through and fill this table out for you. All right, so based on this table, so the limit as x approaches negative infinity. So as these numbers start getting bigger and bigger and bigger, what do you notice about these values right there? Well, they're getting closer and closer to a certain number, obviously never touching that number, which would be 2. Okay, it's getting closer and closer and closer. Then, likewise, as the numbers are getting larger and larger this way, so approaching positive infinity, these numbers are getting closer and closer to the same number, which is 2. So you can see here, as the graph, as x approaches negative infinity, okay, so as this graph, as we start traveling this graph going this way, we can see that these values are getting closer and closer and closer. So if this is going to travel, it's just going to kind of level right off. That way, almost getting to 2, but never touching or crossing 2 by definition of that asymptote. And so, and another thing to kind of sort of note is that these values are approaching 2 from the bottom. So those are values that are less than 2. So that it's approaching y equals positive, or y equals 2 through values of that are, oh, so not x less than 2, sorry, that are, I don't know why I wrote x, sorry, that are through values that are just less than 2. It's like 1.999999999. Those numbers, so below 2. So then likewise on the right side, as x approaches positive infinity this way, okay, it's still approaching, same thing, except we're approaching y equals 2 through values that are greater than 2. So like 2.000001, greater than 2. So those get very, very, very close to 2, but never obviously touches 2. Okay, so let's look again as x approaches negative 3. Okay, so this is something we want to pay kind of close attention to. So as x approaches positive 3, so you can see that I'm getting closer and closer to negative 3 this way, and I'm getting closer and closer to negative 3 this way, but I don't have anything at negative 3 because it's going to be undefined at that point. It's not going to be defined at that point because we have that hole. So let's look at the table of values here. So as you can see, as these two come together at negative 3, so as these two values kind of converge to negative 3, you can see that these numbers are getting really, really, really close to 1.167, which is also, you guessed it, 7/6. So same thing on the other side as it approaches the values from the right side. So numbers that are less than negative 3, those are going to be 1.167, sorry. And that is, again, 7/6. So you can see that they're both approaching the same number. So we have basically, so the numerical analysis for this graph is that we have, they both approach 7/6, even though it's not defined at negative 3.76. We would call that a point of discontinuity. That's a lot. That's a big word, discontinuity. But they're still approaching the same number, which is fine. All right, so now we have one more here that we're going to look at as x approaches 3. I'm going to fill in that table for you now. Okay, so notice that we would have technically 3 right here. So as we approach 3 from the left side, values that are less than 3 here, notice that our numbers are getting very, very, very large in the negative direction. So as it approaches the 3 from the left with the negative numbers that are less than 3, that's going to be negative infinity. Those numbers are getting very, very, very large. You're probably, I mean, I'm not going to say never, but you probably won't ever have like a number that would be out there that you're going to see, oh yeah, that it approaches 5,000. Like, that's probably not going to be it. So just kind of look out for that. But I'm not going to say never, but very rarely would you have that. And then as your graph approaches 3 from the right side, so all values that are above 3 or greater than 3 are going to be, they get big really, really, really fast. So when you go from 3.1 to 3.01, it's 10 times, almost 10 times as bigger, and then like again and again. So therefore, I'm going to have this approach as positive infinity. Again, you're not going to see a big jump like that and it not really start leveling off into some sort of number. Like, it's not going to like be like, oh, it's going to get up from 4,000 to 9,000, and then our limit's going to be 9,000. So like, you're going to see it starting to taper off when you see a limit not in behavior. And so basically, as what we notice from these values are going to get really, really large in the negative direction as we approach 3 from the left side. And then as we approach 3 from the right side here, you're going to see our numbers get very, 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 very large very quickly, as you saw. Okay. So that's basically kind of what a limit means. So as a number, as we approach a certain X value, what does Y do? Is essentially what that's asking. So as we approach, in this instance, 3 in the X value, what is Y doing? That's the whole premise of the limit. So that's just kind of defining limits. So a lot of your practice is just going to be looking at the graph. And so looking at this graph, maybe even having to fill in a table for it and being able to evaluate these limits based on a graph. Just right now, looking at the limit notation and being able to address that there.